Up to this point, we discussed the instability of certain nuclei of atoms, and we discussed the idea of radioactive decay. We looked specifically at alpha decay, which basically takes place when our nuclei is unstable, and so that nuclei basically disintegrates into a more stable atom, and in the process, it releases an alpha particle from the nucleus of that unstable atom. Now, if certain atoms have naturally unstable nuclei, why do they persist to exist in nature for long periods of time? And why don't they simply decay instantaneously? For example, if we examine the unstable uranium-232 atom, we'll see that this type of atom does in fact undergo alpha decay because it's unstable, but it will take about 68.9 years for half of the initial amount of uranium to actually decay. The question is, why does it take so long if the nucleus of our uranium atom is so unstable? So the fact that it takes our unstable nuclei such a long time to actually disintegrate or decay basically means there must be some type of energy barrier that is present and which does not allow the alpha particle to actually escape from the nucleus and into the environment around that nucleus. So, let's look at the following diagram that basically describes our uranium nucleus. So basically we have the nucleus that consists of our nucleons, the protons, and neutrons. Now our alpha particle is found somewhere within this region. Remember, an alpha particle is basically a combination, a bundle of two protons and two neutrons that are held together by strong and weak nuclear forces. Now, how exactly does our alpha particle actually get from the inside of the nucleus to the outside? So in order for an alpha particle inside the nucleus of our atom to escape that nucleus, it basically must overcome the attractive nuclear forces, the weak and the strong nuclear forces of the other nucleons inside our atom. And these forces are very, very strong. So we can basically imagine that the alpha particle moves about a very small space inside the nucleus as shown here, and as it moves, it has a certain quantity of constant energy. Now basically, this small amount of energy that our alpha particle has as a result of its motion is very small compared to the attractive forces that basically create the energy barrier that basically doesn't allow that alpha particle to leave. So that basically means that the alpha particles are trapped inside this finite potential well. So we can basically imagine that the alpha particle inside the nucleus is found inside a finite potential well, also known as a rigid box. And that is basically described in the following diagram. So let's suppose the y-axis is our potential energy U and the x-axis represents the distance r away from the center of our nucleus of that atom. Now basically this region here corresponds to our alpha particle being inside this small space inside our finite potential well. This vertical line corresponds to the attractive forces, the weak nuclear forces, and the strong nuclear forces that basically attract our alpha particle to the other nucleons found inside our nucleus. And because these forces act over very short distances, we see that when the alpha particle is found between these two regions, these forces are so great that the alpha particle is essentially trapped inside that particular region. Now this red dashed line corresponds to the energy of our alpha particle, and notice it's constant. So this corresponds to very negative potential energy because these attractive nuclear forces basically stabilize that alpha particle and the entire nucleus as a whole. Now, so we have this curve here as well, and this curve basically corresponds to the electrical repulsive forces that exist as a result of all these protons found inside our nucleus. And this entire region, this point here, corresponds to the energy barrier that must be overcome as a result of these strong and weak nuclear forces found inside our nucleus, inside that finite potential well. So we see that generally speaking, because the total energy E of our alpha particle is less than this energy barrier as a result of these strong and weak nuclear forces inside our nucleus, because this is larger than this, our alpha particle cannot actually readily escape into the environment, which is shown by this region here. So, once again, this diagram describes the potential well in which the alpha particle is found inside the nucleus of our atom. Now, the horizontal line, this line here, corresponds to the attractive nuclear forces, while this exponential line or curve corresponds to the repulsive electrical forces due to the other protons found in our nucleus. So basically, if the alpha particle, which is found within this region, somehow gains enough energy, as soon as it basically overcomes this barrier, the strong and weak nuclear forces will basically decrease dramatically, because those forces only act over very short distances, and so these forces only exist within this region. So once our alpha particle escapes this barrier, the only forces that our alpha particle will feel are the electric repulsive forces as a result of those protons in the nucleus. So as soon as it overcomes this barrier, it will basically repel as a result of those protons, and it will move outside in the following manner. Now the question is, how exactly does our alpha particle actually gain enough energy to overcome this barrier? So first, let's look at the following paragraph, which is what we discussed just now. So, recall that the strong nuclear forces act over very short distances. Therefore, we can imagine that the alpha particle is stuck within the potential well that begins at r equals 0, the origin, and ends at the point r equals 1. That is, since the energy of the alpha particle is less than the energy needed to overcome the strong and weak nuclear forces given by this barrier here, it cannot escape into that environment. The question is, well, if it can't escape, if it can't actually overcome these forces, how does our alpha particle actually escape? And the answer lies in a concept that comes from quantum mechanics known as quantum tunneling. So, however, based on quantum mechanics, there is a small probability, a non-zero probability, that our alpha particle can escape into the environment and tunnel through the energy barrier from point 1 to point 2, even though its energy isn't great enough. This idea in which energy is momentarily not conserved for some amount of time is known as quantum tunneling, and we discussed this in our lecture on infinite and finite potential wells. So basically, quantum tunneling can be explained by using Heisenberg's uncertainty principle that deals with energy and time. So basically, this equation tells us that energy doesn't have to be conserved, so some amount of energy doesn't have to be conserved as long as that takes place over a very small period of time. So basically, delta E in this case corresponds to this change in energy, the energy difference between our barrier and how much energy that particle actually has. So basically, even though that alpha particle doesn't have enough energy to overcome this entire barrier, our energy doesn't have to be conserved as long as this distance that our object has to travel, our particle has to travel, requires a very small amount of time to actually travel. So delta E corresponds to the height difference in energy, this energy here, and the time delta T corresponds to the time it takes for our alpha particle to actually tunnel from point 1 to point 2. So basically, as long as this time interval is small, and as long as this delta E is small, our alpha particle can basically overcome and tunnel through this entire region, even though energy will momentarily not be conserved. So this idea is known as quantum tunneling. So basically, the higher this energy barrier is and the longer this distance is, the longer it takes our unstable nucleus to actually decay. And so the greater this barrier is and the greater this distance is, the more time it will take our unstable atom to actually decay into a more stable atom and release that alpha particle.